you should be able to see my screen over here. And what we've been doing is we've been looking at objects that look like this. And if you think about what that means, this means where the function, and when I say the function, I'm really talking about the y values, look like they are going as x gets close to a, right? So that's not the best handwriting in the world, I can see, but that's what this left-hand side is all about. It's not what is the function value, it's where does the function value look like it's going. When you look at the right, this thing on the right over here, this is saying this is what the function actually is at x equal to a. So this side is saying, hey, where does the function look like it's going? This side is saying, hey, this is what the function actually is. And when those two things are actually equal to each other, then we say, so if this is true, then we say f is continuous at a. Okay. So what we're talking about in section 1.8. Oh, hold on, let me turn on the transcript here. Okay. So what we're trying to say in section 1.8 is we want to talk about the continuity of a function. So we start off by talking about the continuity at a point, and that's what this is about. Then if something is continuous on a whole range of points, then we can write sort of an interval where it's continuous. Okay, so let's say I drew a picture that looks like this for you. Let's say that we got like 1, 2, 3, 4, 1, 2, 3, like this. And then let's say let me copy this picture. So let me copy it 3 times. So let's copy this guy, put it here, and let's put it here as well. Okay. So let's say that I drew the following picture for you. Let's say that I have an open circle at 2. It kind of comes like this. I put a closed circle over here, and then it comes like this. Oh, wait, you know what? Sure, let's do it like this. Okay. Then when I look at this picture, to me, it looks like it's going to be continuous everywhere except at one point. And the reason why is for all these other points, for all these points to the left of 2 and all these points to the right of 2, the function looks like it's going to the value that it actually is. All right. Another way to think of that is I can draw it, I can draw the function without lifting my pen off the paper. Okay, so this is one way that you can think about being continuous, not just at a point, but like on an interval. So when this thing in red is referring to sort of, oh, is it continuous at an interval? So when you look over here, I can go to 2, but then when I get to 2, I have to lift my pen off the paper and then put it back down to continue drawing my graph. So does anyone know what type of discontinuity we call this is? You can either just say it out loud or you can type it in the chat box. This type of discontinuity has a name. If you saw the video, you might know what that is. Anyone? That's right, Rocky. This is a jump discontinuity. Okay. Let me draw another picture. Let's say I drew a picture that looks like this. So this guy comes like here. Oops, sorry, I meant to do that in blue, my bad. This guy comes like this. This guy comes over here like here. 2, put a circle, and then we come over here. This picture looks a lot better than the first picture, right? In other words, it looks like I'm going along this path, and you know what? It's almost like I could continue on the path. I just have to lift my pen off the paper for a split second and then continue on the other side. So it's just kind of one point where it fails to be continuous. That's true over here on this first picture as well, but this picture is fundamentally different from this picture. So this type of picture also has a name. And does anyone remember what? That's right, that's removable. So why is it called removable? Let me first identify this as removable. So this is removable. I might have misspelled that. According to you guys, I misspelled it. I need to get rid of that E there. Removable. Okay. So how do I know that it's removable? When I think of removable, I think I can fix it. And the way that I can fix it is I can simply redefine my function at a single point. And when I redefine my function to be equal to 2 at 2, then it becomes continuous. Okay, so I'm going to delete that because now it's continuous and I have the word removable there. But that's the idea. The idea is for removable, we can make it continuous. We can make continuous by redefining f of a. So I'm going to show you some numerical examples just momentarily, but I just wanted to do a couple more, just a quick review of the video with you. So if I have something that looks like this, and maybe this guy comes up like this, and this guy comes up like this, or, you know, it could go like this, it could come down like this, and this guy could come up like this. These two guys are examples of something that we call an infinite discontinuity, right? So this is infinite. In other words, I'm trying to graph this guy. When I get to 2, I definitely have to lift my pen to continue drawing the graph on the other side. But when I take the limit coming from one of the two sides, in this case, it's both of the two sides, it's going to be an infinite limit, right? So infinite discontinuities involve infinite limits. These involve infinite limits. Okay. So a lot of what we had talked about on the video is really working with this type of stuff. Then we also saw, well, let me just go over the worksheet with you. So let's do this here. So I think today is 9-3. Yes. Okay. So when I have this this worksheet over here, this looks like 3 kind of separate conditions, but in reality, the actual definition is just this last part. So this is the real definition. The first 2 parts are just saying that it exists. Okay, that the right-hand side exists and the left-hand side exists. That allows us to create this equation. But this highlighted thing is the real definition that we're going to be working with. All right. So let's take a look at example 1 together. We want to determine whether this function is continuous at the point x equal to -2. So what I'm going to do is I'm going to calculate the limit as x goes to -2, x squared minus 4 over x plus 2. So my first question for you is, do you guys recognize what type of function this is? This guy's a name. It's not a polynomial. Does anyone know what this is called? Just checking in. You type your answer in the chat box if you do. Piecewise, Simon, this one's not piecewise. That's going to be number 2. Number 2 is in piece. Parabola, Wilson, the top is a parabola, the bottom is not. The top is a difference of 2 squares. Mario, I need to use that in 2 seconds. This is something called a rational function. Yes, Stephanie, rational. So rational just means a polynomial over a polynomial. So as we know, for a rational function, I can just use the direct substitution property to evaluate the limit. But when I try to plug a -2 in here, I'm going to get a 4 minus 4, which is 0. And then I'm going to get a -2 plus 2, which is 0. So we don't have an infinite limit in this case. We have a 0 over 0 type limit. So on Wednesday, I plan to ask you a bunch of different algebra techniques. And I wanted to know which of those techniques did I want to use? Did I want to use direct substitution property, factoring, multiplying by the conjugate, simplifying, taking one-sided limits, squeeze theorem? Which one of those things did you want to try for this rational function? Does anyone have any feeling? Simplifying, factoring. I like factoring. I think Mario already mentioned that this was a difference of 2 squares. So let me write this as the limit as x goes to -2. I can write the numerator as x plus 2, x minus 2. And I can write the denominator as x plus 2 like this. And then we can see that I can cancel one term from the numerator and one term from the denominator like that. So then in the end, that allows me to just plug in a -2 and I get a -4 like this. Okay. So that's going to be my answer for the left-hand side. Remember, maybe I shouldn't highlight it, it's too soon. So that's just the left-hand side that I calculated over here. Now, if I calculate what the right-hand side is, what is f of -2 going to be equal to? When I look at my function, do you see how -2 is not inside the domain? So this guy is actually undefined. So this one is not continuous. So just to make it perfectly clear, this is the left-hand side of this definition up above here. This is the right-hand side. And they're not equal. From one side, it's -4. From the other side, it's undefined. So my answer would be this is not continuous. I'll say at x equal to -2. Is there any questions about example 1 here? No questions. I have a question for you, actually. After I factored and I simplified, I got an equation. I got this x minus 2. And what that means is that's really like y is equal to x minus 2. What kind of object is this guy? Parabola? No.
A line.
It's a line. That's right, Rocky. It's a line. And I can graph this line. I know I can draw a little set of axes over here. And here's -1, here's -2. Here's -1, -2, -3, -4, like this. Okay. And when I go to graph this line, I'll do it in green. I'm going to put an open circle at -2 because we know that the limit doesn't exist at -2. But this is a line of slope 1 that's going through the y-intercept of -2. So this line kind of looks like this. Does that make sense? It's got this, it's a line with a hole in it. The reason why we have the hole at -2 is because the function is undefined at -2, because -2 is not in the denominator. Does that make sense to everybody? Did anyone have any questions about this? All right. So just to make sure that we're clear, based on what I said at the very beginning of class, which type of discontinuity is this? Is this going to be removable? Is this going to be jump? Or is this going to be infinite?
Removable.
It's removable, which means I can redefine it at a single point and make it continuous. So just to make sure it's obvious, if I redefine f of -2, instead of being undefined, if I made it equal to -4, that would be like me just plugging in that hole, and now the whole function is continuous. Does that make sense? So when you're calculating all these types of limits over here, a lot of times it reduces to something like a line, and then you can really make it continuous by redefining it on that missing point.